check and make sure sound is up. Okay, so what I wanted to do today is just kind of review the concept and the problem types associated with Bernoulli's equation. Okay, so if we review Bernoulli's equation, it sits right here. It's basically nothing more than the kinetic energy, the potential energy, if you look at it, mgh per unit volume, 1/2 mv squared per unit volume, and actually F dotted with some distance x per unit volume. So with this, it's pretty apparent that this is nothing more than an energy equation, and in fact that's all it is. And so what happens is if you're at some spot in the fluid, you flow and you can get to some other spot too, then the energy should be the same if the flow is, let me get rid of this, inviscid. Okay, the word inviscid and no losses can be used interchangeably because the losses occur because of the viscosity. The viscosity is zero, or assumed to be zero. It never really is zero. Then this equation works well. Otherwise, you've got to consider the losses in there, which we'll do in chapter 8. Now, there are situations in which, even if you include losses, it can work fine. Here's a particular case. If you have a flow situation where you have a constriction and say you're checking the pressure difference between these 2 points, and the distance between these two is very, very small, there's not as much location or time or distance to have significant losses. Compare that to a situation in which maybe you have a large pipe, it goes 1,000 feet, turns, comes back, and you're looking for the pressure differences across this thing. It's a long, long distance to travel, and the losses will be eaten up as you go through this pipe. So short distances, pressure reading and flow reading devices are okay with this. He talks about free jets. But what I want to do, okay, so what he's doing here is he's tracking, I'm just going to give kind of an overview. He's tracking the fact that this point could end up there. If you look at 3, there could be no or little velocity here. So this might exist in mostly a static pressure condition. Here he's talking about the fact that the flow can be large and fast enough so that it has a constriction here, where this area is slightly smaller than that. Okay, he talks about this. Okay, you can see this. This is an analogy he's making to the kinetic energy. But let's look. Okay, there's another thing that might happen. And what might happen is the flow might go from in this case, a larger velocity to, a larger area to a smaller area. So you could say area large to area small. So in this particular situation, you have the m dots the same through the whole thing. So in fact, there's a slow velocity and then a faster velocity. Continuity equation, you've seen that before, not anything new to you. So let's look at one of the particular problems which I find to be very interesting, which is this one. So here's a case, and there's others like this too. Here's a case in which, and I worked a problem like this the other day, where you basically go from 1 to 2 using Bernoulli's equation. You do 1 to 2 using Bernoulli's through the flow. That's what he did right here. He went from 1 to 2 using Bernoulli. He also recognized that at 2, smaller diameter than back at 1. So therefore he had to use continuity, which continuity, okay, you saw a lot in thermo with rho AV. M dots equal to rho A and V. Turns out most of the time through this book, there's not going to be a phase change. And we're thinking mostly incompressible. So what he does is he basically recognizes that this is a density times a volumetric flow rate, which usually it's listed as just Q, where this could be cubic feet per second, and this would be, in this particular case, slugs per cubic feet. I'm trying to get this. So these would, that's supposed to be cubic. So these would cancel and you get m dot, slugs per second. Now, if you feel more comfortable with kilograms per meter to the cube and meter to cubes per second, where this would be the Q, and this is your density, you get the same thing, kilograms per second. Now that you've done that basically you can replace one of the velocities with the other velocity, but that doesn't get you anywhere. You have to strap on this pressure reading device. If you don't, big deal. You can't do anything. So what you do with it, you go in, and I think he starts, okay, so here's what the next step, okay, you need to use the manometer that you have attached to it. So what you've got to do is, now you're working a different set of equations. You basically come up and you're going a vertical distance here through the flow, through the manometer. You can stop or not stop here, but you continually go through this until you reach point 2. So what did he do? He started at 1. He went up. Through this fluid. Okay, let's look at what he did. He went up through this fluid, this blue, whatever this is, that distance. This particular point, he's at 1. So here, let's label this. So no, let's label it as A. So here is the pressure at A. Then he went up this distance. Oh, wait. Sorry. He went up L, stopped right there. That became B. So here's your B. Then he went up further and say let's call that C. So here's your pressure at C is all of this. So now it's getting very cramped here. So your pressure C includes all this. Then he went up and back down, and right here he was basically the same as pressure at C. Now he goes down, increasing pressure through this fluid, which is so much heavier than water. So this indicates to me that he's assuming that this thing is water. Yes, he says it's water. And now he goes down again this distance to get to the final state at 2. So what he's done is he's taken a journey. And you can list it. He went up through this fluid, this distance, continued to go up through this fluid this distance, continued to go up through this fluid this distance. Oops, now he turned and went down through this fluid this distance, went down through this fluid this distance, and arrived at P2. Then he worked out the math and found out that he can basically write P1 minus P2 as this. What does he do then? He injects it back here, because what did he do here? He took this, he moved this to the other side to attach itself to this. He took the 1/2 row and he converted V2. So he left these. So this is his conversion here. So if you're going to leave V2 in here, you're going to substitute in V1. So you're going to say 1/2 row V1. Well, what is this? Okay, so it's A. Okay, let me see if I can write this with the space I've got. B2 A2 over A1. So he injects this into here, and that's why you see, because you have to square this. If you're going to square it and square it and square it, the V1 squared can go back in here. So you will get a squared 1 minus the distance of the area squared. That's what's the A1. Then you can put them both together and take a look at how this and these terms combine together. And what you'll notice, and this, you have to stare at this a minute. Okay, here, I'm going to try my best to accentuate this using this marker. So you're basically taking this, putting it in for here. So on the left hand side, you're going to put this equation. On the right hand side, you're going to put that. Now go back to my marker. If you look on the right hand side of the equation, you get this. On the left hand side of the equation, you get that. Immediately, you can see that this one will just be copied down, and this one will be just copied down. And before you know it, you can basically, and this is what you're going to do, you're going to attach a device like this, read the H, and determine the information from the H. Or, you know, that's what you're going to do in the real world. He's basically telling you, he wanted you, let's see. Well, he didn't say what he wanted to do, but in essence, sometimes people don't represent it this way. They represent it more. I mean, if you really think about what you're trying to do, you are coming in and you have H and you've read it, but what you're really looking for is that. So if you want to look at that, you would have H2 here. This might seem familiar. 2GH, 1 minus SG. So I took the 2GH, moved it over, then move this underneath over there. Now, you take the square root. So if I took the square root now, move it back. So if I took the square root of that, multiply it times A2. Now this is what you would normally do. You would know, so here's what you would know. You would know the area of the two pipes. You would know the fluid you put in. You would be able to read the gravity. I mean, not read the gravity, read the height, know the gravity. And if you knew A1 and A2 here, you'd know A2 there. And out of that, you can write, this is what you're basically doing, Q as a function of H. And really, the other terms you know. So essentially, that's what you're doing. In other words, you would know what fluid you put in there. You would know the geometry. You would know the gravity constant wherever you were. and you would know the geometry there. So essentially that's more like, this is more like what you would actually do with this in the real world. Now as you go further through this, you start noticing, okay, this is something that I think I talked about a while back, is you can actually put a pipe down through here and put it in a vat of chemical or soap to wash your car. And what you notice is that you'll get to the point where you will create a vacuum on it, and that vacuum will suck the stuff up there. However, if you don't put a pipe, then what you could realize is you got yourself down to the vapor pressure. Okay. Case in point, vapor pressure of saturation are the same thing. In other words, if you go back and look at the pressure vapor at, say, 80 degrees Fahrenheit, you'll find that it's the same thing as the saturation pressure at 80 degrees Fahrenheit. Meaning that if you drew it below that pressure, the water was sitting in a vat, and you put a vacuum pump on it, and it was sitting at 80 degrees, and you started drawing it, and you drew it below that pressure, it would start boiling immediately. It would boil at 80 degrees, and I could show you videos to that effect. And so what happens is it instantly turns to vapor. And that's kind of what this is talking about with cavitation. If you start thinking about it, you know, this propeller is going to create a large pressure on the back side of here to propel the boat this way. But on the back side of this blade, you'll see originating off the back side of the blade is low pressure. If you got it too low, it starts immediately boiling while touching the surface of the propeller. And believe it or not, what it will do is chew that propeller to pieces. And so here he's talking about just siphons, you know, the fact that, you know, if you write Bernoulli's equation between this point, well, and you can go down this point if you wanted to, and this, you could set yourself up to P, the elevation. Usually I write it, yeah, I write it that way. The elevation, 1, 2, and 3. Okay, so as it exits out of here, as it exits out of there, it's nothing. As it's up here, nothing. You don't know what P2 is here. You can, okay, so here, let's use our datum as down here. So this, the datum was there. It would be 0 for 3. It would be 5 and 15 or 20 for 1. It would be some H for 2. Now the velocity at the very top, we're going to assume that it's pretty slow, so that would be 0. Immediately you realize I can get my energy state from here. I know this, this, and this. So at this particular point, I can actually go in and solve, I guess I'll call it V3. So what does he do? He does exactly that thing. First thing he does is V3. Next thing he's probably wanting to do, he probably wants to make sure that this doesn't get to vapor pressure, my guess is. So, all right, so from table, the vapor pressure of water at 60 degrees is 0.256 psi. You can just replace that with saturation pressure. So I don't know why there's a change in the way they think things, but at this point, he wants to know what this needs to be. So if that's the case, then P2 would be, hang on, P2 would be 0.356. Once you found 3, guess what? The diameter of the pipe didn't change. So guess what? That's the same value. So at this point, you can say to yourself, I could write Bernoulli's equation between here. Well, here's what you actually do. First thing you do is you write Bernoulli's equation from here to here to fill out or answer the question, what is that? Once you figure that out, you copy it to here. Then, I would write Bernoulli's equation between here and here and work that one, although it doesn't really matter because you already know that the constant, it's going to be, in my case, it's going to be 20 times the gamma. Then you're solving for H. Okay, in a flow rate measurement device, they use this concept. In other words, there's Orifice meters. This is very common. This is very, very common. A little bit less common, but it's still out there, where you're turning the flow. In either case, what you're doing is constricting it, and you're measuring the pressure between here and some spot up here in all of them. Venturis generally provide the lowest amount of losses between 1 and 2. Here you can see some swirling, and that swirling is going to create a little losses. You go through this, and what you're doing is writing Bernoulli's equation between the one spot and the second spot, first spot and second. You're recognizing that there's an area change between here and here, and then you're injecting this to take care of the velocities, and below, believe it or not, this is the same equation, kind of, that we had from before. The only difference is this is listed as P1 minus P2. Now, how do you get the P1 minus P2? You can either just put a gauge here and read the pressure off, or you can do like they did in that case a minute ago. They drilled a hole in the side of the pipe, put a tube, and filled it up with some sort of fluid, and since it's creating a vacuum here, this heavy red fluid basically has a height difference here, and from that height difference you can basically find delta P as a function of that height difference through manometer equation, and that's what we did before. So here's a typical case. Now what he's done is he's cheated and basically saying, I just got a dial that tells me that pressure difference. That's kind of, I don't like that, but determine the range of the pressure differences between here and here with the flow rates between this and like that. So he goes in, he writes Bernoulli's between 1 and 2, takes the continuity between 1 and 2. He just takes the equation, 320, okay. So he takes this equation, rearranges it, but to get that equation, he wrote Bernoulli's between 1 and 2, used the continuity between 1 and 2, came up with that equation. Then he basically goes in and puts in some of his numbers. Okay, so this is something you might want to pay attention to. This seems to be a problem with a lot of people. Take the density of water, the specific gravity of the fluid that you're in, to get the density of the fluid that you're in. Excuse me. He goes in, takes the area difference, takes his pressure differences, and then goes through, and what he does is he looks at the flow rate across the x-axis and the pressure difference across the y. I think I would have flipped those, but that's okay. So you see that it's quadratic. Well, that makes sense. Look, there's a quadratic term right there. And then what did you do next? Well, we did something along this way. These are the sluice gates, they call. I wrote this equation last time where we started with z1 at some velocity 1. We end up with z2 times velocity 2. he wrote Bernoulli's between 1 and 2. Then you notice the area difference between them, that this is a lot tinier area than here the way it's drawn, and you use continuity to offset to find V2, V1, height 1, and height 2. Makes sense if you look at it. Then what you can do is, now he's looking for the Q. I think I did it in a problem where I was looking for the V. He ends up with this equation. Now, he should go down. Okay, he stops at this point, but if you were given this, okay, here's one of the strange things here. And this is, you can see this in the problem I did. If you were given this, and you're given this, and you're actually trying to find V2 accompanied with C2, you'll get two solutions. You'll get actually three, but one is a negative value. It's not possible. The other is the flow went back up, came to the same height. The second is there's a particular location it goes to if there is no loss of energy, in which the energy at this state is the same as the energy at that state, if there's no loss in energy. So we did that. Okay, then he's going through doing some cases here. Now you can do the same thing here over the top. There is a thing called a V-notch weir, which we have, a triangular weir in the lab. So this is a particular, I'll go ahead and do this one thing and then call it quits. This is a particularly powerful thought process. This is basically a thought that came from civil engineering. Okay, so let's look at Bernoulli's equation we saw before. P plus gamma z plus rho v squared over 2. We rewrite it, and what we do is divide by gamma. Before, the units of this equation were pressure. Now, if you divide by gamma, it becomes a height. So think about this, pounds per square inch, and we're going to divide by, okay, so let's make that feet. You're going to divide by gamma, which is, pounds per cubic foot. Comes up with units of height. And it turns out that's a very, very convenient way to view things, because you can look and see a height difference. You can visually see it. If this elevation of water is higher than that, you can see water always kind of flows downhill. So as it's flowing downhill, it's picking up speed, so somebody can say, hey, let's think about this from a height perspective. So here's what we'll do. We're going to think of this as the total energy height. As this water or whatever is coming through here, there's a couple of things here. This is a static pressure here, but you see it stagnates right here, so that extra kinetic energy shoves this pipe a little higher. So what is it saying? Hey, it's saying this is the kinetic energy. This right here, let me erase this. This height from here to that is the pressure energy, and this is the elevation above what you've picked as a datum. So when the water flows up to this point, and it's right here, what happens? Well, the Z went from here to here, and so the pressure, guess what the pressure did? It declined a little bit. So the distance from here to here, a little smaller, and guess what happened here? The area got smaller forcing the velocity to get a little bigger. So its velocity became larger here than here. And then finally, it became a smaller diameter here. I'm going to get rid of this. As it became a smaller diameter there, then guess what happened? So kinetic energy was here, the velocity increased and increased again. Likewise, this is physically, you can see it. This is the height, Z2, to that particular point. The water came in here and stagnated, so its kinetic energy was given up to push this up a little higher. Kinetic energy just, it's still in full speed past this tube. So what you get is this is the kinetic energy portion, this is the pressure portion, this is the elevation portion. Now if you think about it, the water, he didn't show the rest, but let's say it just went up into a vat. Now eventually the water over here, it'll get in here and then it will die off. So it turns out that the height of the water, if there were no losses, this is where it would end up at. Because right here, you would have the total elevation, Z top of the water. You would have pressure equaling to 0. So this pressure would drop down to 0. And you would have the velocity equal to 0. So this would be where if there were no losses, this would be where the water would go up to. So he has two terms here. Let me get to these terms. And this is a civil engineering concept, but it's also very logical. You have what's called the hydraulic grade line, and you have the energy line. The hydraulic grade line is basically the total energy without the velocity attached to it. The hydraulic part. In other words, it's basically P over gamma plus the Z. So it's basically the elevation of the water above some datum, and then this pressure over gamma, the pressure state wherever you're at there, whether it be here, wherever you're at. So this is typically called the hydraulic grade line. Energy grade line is the velocity attached to it. Here's why they separated this. What happens if you lost energy? If you lost energy, and you're basically looking at this will kind of pretty much remain fixed. But what's going to happen is you're going to degrade your velocity. So if you do have losses, here's what will happen. Hang on. So what he's shown is this energy line remains fixed, right? As the flow is moving across. But if you did have losses, what you would have is this basically coming down. And what would happen is, I'm trying to show this, you would have this coming out into a lake in which the losses created the water level being a little lower. And this can actually happen. And here's what he's showing this along the way. Okay, so if you look at it, you have the energy level, or energy, okay, I don't like that, but energy line, energy level, energy line, and hydraulic grade line. So you started up here, you had nothing. So all of it existed, all of the energy existed in the height of the water up here, i.e. a water supply system for your city, a big tube up there, they're vented on the top somehow. And it goes down and eventually comes to your faucet. So what happens is all of a sudden you're delivering water down the pipe. You have to have velocity to get the water from point 1 to point 3. So what happens is you have a velocity here. You'll have a pressure, and basically these two will offset, come out to be called the hydraulic grade line. then what happens? You pick up speed, and as you pick up speed more, hydraulic grade line drops way off to the point where it comes out the exit at P is equal to 0. Now, this is not really what happens, but here's kind of what happens. So first of all, the energy line drops off. What elevation, how quick it drops off, depends on the flow and several other factors. But why is it being dropped off? We'll find out later that through a pipe, it's basically proportional to V squared. So, in other words, the losses are proportional to this. They're not proportional to that or that. So, in essence, what happens is energy is dropped off. The velocity does remain fixed in here, but the whole thing starts dropping. And so this last section, for example, okay, let's just consider this. Think about this. Bernoulli's equation back at this point would tell you the pressure here has got to equal the pressure here, because the velocity at this point is the same all the way down this tube. And guess what? The elevation's the same. So wait a minute. What's going on here? So the velocity is the same. So essentially what happens is when he starts talking about the pressure, he comes down to this point. Well, what actually happens to this, let me just address this part of the pipe. This thing right here is P, well, I won't call it 2, I'll just call it P, how about point A, P point A over gamma. Starts right here, and then it declines off and ends up exiting the pipe at P3 equals 0. But back here at PA, it's, I don't know how much greater than 0, but it is greater than 0. So in fact, as you look at this, you're going to have changes in pressure because of this. Otherwise, logically, if you set this on the table, or say, put your head on this, and you decided to use your lungs to blow air through here, and it's a straw, and this is location 1 and this is location 2. One, two. Then continuity will tell you that because this straw didn't change in diameter, velocities can be canceled. If it's elevated the same, then this Bernoulli's equation tells you P1 is equal to P2. So this means you could pull that straw out mathematically, put it on the table, pressure on one end is equal to pressure of 2, and air would just naturally blow through there. Not going to happen. So in fact, what you've got in the real world, you've got minus a loss here. So then you have an energy, whoops, let's do this. P1 minus some sort of loss of pressure is equal to P2. So this means P1 could be, say, 10 minus 1, say minus 1 psi might, well, in this particular case, you would have a 10 psi, you'd have to have a 10 psi loss to get to a 0 because this is the exit pressure. So whatever the pressure is back here, you're going to lose every bit of it as you get to the exit. But you're not going to lose any velocity, you're not going to lose any elevation. So that's where the hydraulic grade line and the energy line, you'll see them drawn actually on drawings that most civils are professionally or PEs, and so they produce a lot of drawings. Okay, so he's talking about compressibility effects. So effectively, we're done with chapter 3. You should be able to do any of the problems that are given to you. I'm not going to give you any incompressible anyway. So we'll call it quits here. Next chapter is chapter 4. And it's setting up fluid kinematics. And these are all good. We'll talk about them a bit, but eventually the biggest key that comes out of here is down here where we get to Reynolds transport equations, which are somewhere, well, it starts with the control volume and system representation. And so this is kind of where I'll focus my energy from here down. I'll start in on that Monday. So with that, I'm going to call it good.